Wilkinson, and I'm still director of the DiRAC HPC facility. I'm going to mess up the video because I tend to walk up and down, so
That's okay. I'll be on your slides a lot too.
Yeah, I'll pretend to stand at the podium and then you can Photoshop me in. First of all, I'd like to echo what Gilad said. Welcome those who weren't here a few minutes ago when I welcomed everybody initially. Thank you all for coming to Leicester, and I hope we have a really useful couple of days at this inaugural HPC AI Advisory Council conference in the UK. What I'll do in this talk is just talk a little bit about the eInfrastructure roadmap for UKRI that's been under development over the last 18 months or so. Many of you will know, will have heard about it, and hopefully this will give you some information and an update on its current status. I should just say, can everybody hear me at the back if I talk at this level? Yeah, fine. So, just to start off, why are we doing all of this? So, in theory research, which is the area that the DiRAC HPC facility supports, computing at HPC is absolutely central. So it's actually one of the main theory research essentially depends on HPC nowadays. You can't do theory research if you're not doing numerical calculations. But the complexity of the calculations and the computational requirements to deliver them is constantly growing. It's been growing for many years and it's going to continue to grow in the future. So that's for several different reasons. Sometimes it's because we're running the same physics or the same equations, but we're running at higher resolution. Often when we go to higher resolution, we have to add in new processes that suddenly move from being sub-grid to being actually on the grid, and so we have to introduce that. And that reflects improvements in the theoretical understanding of the problems that we're looking at. Now we're often coupling models at different scales, so we're looking at systems where you may have things, say, in the context of a galaxy simulation, where material moving around the black hole at the center of a galaxy is operating on timescales of minutes to hours, while stars moving at the edge of the galaxy in the same simulation are changing on timescales of hundreds of millions of years. So you've got these enormous dynamical ranges, and you're trying to couple the physics on very different timescales and length scales. And that example is a galaxy, but it equally applies with suitable normalization to problems like simulations of a jet engine from a whole system simulation. Also now, more increasingly, we want to quantify the uncertainties in the simulations. I don't think that's me. We want to quantify the uncertainties in simulations, not just run one huge hero simulation and then use that simulation as the result, but actually to have run many simulations and have an understanding of how the initial conditions and the assumptions feed into the output that we get. And the key thing is that HPC is a scientific instrument for theory research, and increasingly it's a scientific instrument for all aspects of research across UKRI. And there's a growing requirement that telescopes and other instruments that are generating data, I'll apologize in advance, I'm going to keep using analogies that come from astronomy, but that's just because of my background. So whenever you hear telescope, you can substitute whatever your favorite experimental or data source would be. Facilities that are generating data, be they simulation data or experimental or observational data, often there's too much data to just shift that around, and so we have to do a lot of work to actually do compute locally. So within the DiRAC HPC facility, what we've done in terms of designing our systems, because the HPC services are our scientific instruments, we have to make sure that they're designed by the researchers, so that the researchers are involved in that process, just as you would with a particle physics experiment or a cryo-EM system. You have the researchers involved in designing how the experiments are run. And so the process that we've developed starts off, it basically just follows the scientific method. You start off by writing down what it is you want to do in terms of the science. So we talk to the community, and this is a process we're going to replicate now, or are in the process of replicating across across UKRI. So you write down what you want to do. We get that peer reviewed, so we have a basis for all the future discussions about what systems we need. We then translate that into a technical case, so look at the type of systems and type of services that are needed to deliver that science. That technical case is then peer reviewed. And at that point, we have a good basis for working with our industry partners to make sure that we can actually deliver these systems. So that's the point at which we start discussing, well, what if we want to deliver this type of scientific workflow, what are our options in terms of technical specifications? And in the DiRAC facility, what that's led to is different systems for our different science problems. So we have 3 services spread across 3 sites: Leicester, Cambridge, Durham, and Edinburgh. The Edinburgh system is extreme scaling, or Tesseract, and that is focused on problems like lattice QCD, theory particle physics calculations, and those calculations scale to very large numbers of cores, but only if you have sufficient, scale to very large numbers of cores, and you don't need very much RAM per core in order to do that, but you do need well-designed network topology. On the other end, we have the memory-intensive system, and memory-intensive is focused on cosmological simulations. So these are problems where you're trying to simulate the evolution of the universe, and those simulations scale to large numbers of cores as well, but only if you have enough RAM per core to keep the nodes busy. And in the middle, we have 2 data-intensive systems at Leicester and Cambridge, and these have a range of different architectures, and that's designed for a wider variety of types of problem, but focused on ones particularly where there's a large data set, either a large theoretical data set from a simulation or a large experimental or observational data set. And while you're running your simulations, you're trying to cross-match between your simulation and or calculation and that data set. And having different services and that design process, the reason why we do that is because ultimately our goal is to deliver as much science as we can with the funding that is available. So this is just one way of presenting it, and this I promise is the only bit where I'm going to boast about DiRAC in terms of publications. But this is essentially a plot showing the citations of papers that have been published. So each block of blocks is a year of publication, and the different colored bars are the citations in subsequent years. So the blue bar here is the citations in 2015 of papers published in 2014. And the point to take away is that the papers that are produced from the DiRAC services are generating lots of citations, and they're generating them over an extended period. So they're not just papers that appear, get cited, are shown to be wrong, and are then forgotten about. Though, as I said last week, some of the papers in there will have appeared, been shown to be wrong, and the reason they're still cited is as evidence of how not to solve the problem. But that's the minority. We had the most cited paper published in 2015 in all of astronomy, and we've got getting on for 1,000 papers, actually over 1,000 papers now since 2012. And one thing I'd like to mention because many of our industry partners are here, a new scheme that we've added to the training portfolio for the DiRAC facility is a set of innovation placements. So these are STFC-funded 6-month placements for PhD students or early career postdocs. And the idea is that they do a 6-month placement with you, working on a problem which is not to do with their PhD. That's really the only criterion, is that they be doing a PhD in an STFC-related area, and that when they're working with you, they're not working on their PhD. There's a list of the ones that we filled already. We got 8 initially, we filled 9, and STFC very kindly funded the 9th one. However, if any of you has an idea for a placement, then please get in touch, because there are, if you speak to Jeremy Yates, our Innovation and Technology Director, we can take on more of these. We basically go back to STFC and say we have more ideas. One that I'd highlight is that's going on at the moment is this one in Guy's Hospital, looking at generating a frailty index that can actually be used by clinicians, and that particular one has been very successful in terms of driving that forward so that we can use the techniques that have been developed by various groups within DiRAC and in Guy's Hospital to improve understanding of frailty. So now we come to the roadmap. So the UKRI, as I think all of you probably know, is the umbrella for all the research councils now in the UK. It stands for UK Research and Innovation. And last year they were commissioned by BEIS, that's Business, Energy and Industrial Strategy, the government department that funds UKRI, to produce an infrastructure roadmap for the next decade. And that was in order to support strategic planning for UKRI funding in general. The roadmap has 6 sections: biological sciences, health and food, energy, environmental sciences, physical sciences and engineering, social sciences, arts and humanities, and computational and the infrastructures. And so the first 5 obviously largely follow the main areas of interest of the research councils, and the inclusion as a separate cross-cutting theme of computational and the infrastructures is extremely valuable. So that was people like Susan Morell in EPSOC pushed very hard for that to be included explicitly, and it's given us a great opportunity over the last 18 months to build the case for the infrastructure, supercomputing, and all aspects of computing that are needed in a very explicit way. Now we have to move and get someone to pay for it, but at least it's clear what's required if we want to deliver the scientific roadmap. So the point of the whole roadmap process was to understand what's already available and then see what is needed in terms of infrastructure to support the next 10 years of research. It was also to look at how the existing system services work together or don't, and find ways to make them much more either interconnected, interoperable, or join services together if that's the appropriate approach. The main goal, obviously, is that this would underpin, it's not an actual funding roadmap, but it would underpin decisions in the future about strategic directions for investment, but it would make sure that the infrastructure to support those investments was in place. It would promote the UK as a global leader in research and innovation, and also, crucially, it would be a way of linking to this vision for 2.4% of GDP being invested in R&D by 2027. And that's actually important. It's a very important point that everyone bears in mind, that this link between the UKRI infrastructure roadmap and the R&D investment is essentially, that's why when we're doing a lot of these new projects, we need to be thinking about the innovation side as well. These are the goal within UKRI is obviously to deliver the science programs of the various different communities, but we're also trying to deliver an innovation agenda as well. So that's crucial in all of our thinking for the future. Just to show how important, with this audience I don't need to really show this slide, but I thought I would, because there's one that you might not expect. So this is the result of the landscape analysis, where about 800 different infrastructures across the UK were surveyed, and they were asked questions such as, how important is the infrastructure to what you do? Are you an e-infrastructure provider? And do you think e-infrastructure is going to be important or increasingly important over the next decade? And what you can see is in all, so social sciences and humanities, arts and humanities, physical sciences and engineering, environment, energy, and biological sciences, health and food, everybody says that it is used as a tool. Some areas it's the primary discipline, and in about a third it's not used. The interesting thing is that in, for example, biological sciences, health and food down here, 75% of infrastructure said that e-infrastructure was and data were a tool underpinning their work, and 83% considered that it was going to become increasingly important. So it's obvious, possibly, that it's going to be important, continue to be important for the physical sciences and engineering. But in other sectors like biological sciences, health and food, it's also increasing. And likewise in the social sciences, arts and humanities, that's another area which had a very high response to that question, saying it's going to be important in the future. So in terms of the e-infrastructure side of the roadmap, as I said, it was included explicitly as a cross-cutting theme, and it was divided up into six areas. And for each of these areas, a white paper was written, bringing together what the associated communities across UKRI think are the key aspects. So we've got supercomputing that I'll talk about, data, cloud, software and skills. There's two, one on network infrastructure and one on AAAI, which I won't go into in as much detail, not because they're not important, but just because there's only so many things you can fit in a talk that other people probably want to talk as well. But the key thing is that the AAAI and network infrastructure are absolutely central to making this overall infrastructure useful for not just for academia but also for industry. So we've got to make it that people can move data between systems more easily, and we've got to make it that it's more accessible to industry, and that's where the AAAI side of things becomes very important. And this roadmap, you'll note, doesn't have AI as one of the areas, though AI is mentioned in many of the individual white papers. The reason for that is there is an AI review going on at the moment, and the goal of that is to understand what is the role of AI at the moment in UKRI research, what is it expected to be over the next decade, and what aspects of that need more funding. So there's a process now of joining together there will be a process joining together the outcomes of that review with the roadmaps that have been drawn up in eInfrastructure. So this diagram shows the overall structure of the e-infrastructure, essentially as it is now, but also highlighting some of the key things that need to be developed. So what is important here is in the center you have the researchers. So the key driver for everything within the roadmap is the research that we want to do. And that research is both academic and within industry, and so it also includes innovation. So at the moment it's something like 100,000 researchers in total across UKRI and industry. That's expected to rise by at least a factor of 3 over the next coming years. The network access is central to being able to access the services, and then the software layer is increasingly important. As Gilad mentioned, it used to be that there were lots of, so most people were using tools that they've written themselves. Increasingly, these tools are having to evolve, and in order to exploit the next generations of hardware, an awful lot of software engineering work is needed. And honestly, we're not ready yet. I don't think any community is ready. So that's an area that needs to be supported and encouraged, and a lot of work has to be done to not just provide the relevant expertise, but also to encourage the communities to engage with it. And then around the edge, you have the many different facilities, such as DiRAC, Archer, the Met Office, Jasmine, the Hartree Centre, and all the others. And I just realised there, I've just said all the STFC ones, but you can see them all there. So essentially, this shows all the different types of services that we have now and the different scales. And what we have to make sure is that everything becomes more joined up in a useful way, in the sense that there's an underpin. Whenever there is a scientific workflow that needs to use multiple systems, we want to make it as easy as possible for people to do that. So I think it's no secret to this audience that UK investment is lower than in other countries. So this slide is just to depress everybody further before I lift you up with the optimism of the roadmap. So some time ago, so this is 2011, 2012, we had, the UK wasn't doing too badly relative to others, only Germany was higher. Now there are many other countries of comparable size that are spending more. This plot, by the way, is a plot, it's just one way of showing spending. So it's the combined the combined power of all the non-industrial top 500 systems in each country per unit GDP. But essentially it shows the UK has underinvested now for getting on for a decade. And so that's something that we need to address if we're going to remain competitive. So the vision for the roadmap, so this is supercomputing, and I should have said, what I'm going to do now is go through the various white papers. I'm going to focus on the supercomputing one because of the audience that's here, but I will then talk about the data, software skills and cloud as well, just to emphasize all the work that's been done. And so the next few slides are going to focus on the supercomputing roadmap. So the vision for the supercomputing roadmap is that we have a supercomputing infrastructure that enables world-leading science, enables and supports cross-disciplinary activity, keeps pace with technology developments, is well coordinated, and is underpinned by a long-term strategy. And so all of these things I'll discuss in more detail in the next few slides. But the key thing, and this is a message that came out that was emphasized in all the papers, in all the white papers, was that in order to enable world-leading science and engineering and research, we've got to make sure that the business cases are driven by the science cases, and the technical cases are driven by the science cases. So in all of the services for all the white papers, in all aspects of the infrastructure, we've got to start with what it is we're trying to do from a science perspective or a research perspective, and then go on to see what's the best way to do that. And the other thing that came out in terms of supporting cross-disciplinary activity and enabling world-leading science is there is a danger, because of the underinvestment, of a lack of ambition in, not in every community, but certainly in some, that people are so used. It was actually a challenge at times to get people to think. Gilad mentioned asking for faster horses. Essentially, it was somebody with a horse asked what they want and saying, well, another horse would be nice. I don't even need a faster one, it'd be just nice to have two. And whereas we were saying, well, we have these things, we have these cars, other people have cars, we should really get one of these. And to get people to think, well, what would I do if I had a system that was an order of magnitude bigger rather than, a factor 2 bigger? And that was actually a challenge, but I think we managed to get people to think bigger. So this very wordy slide, and I apologize that this talk is a mixture of very dull, wordy slides and a few nice pictures just to liven things up. But I wanted to make sure that you have a chance to see what the key recommendations were from each of the white papers. Am I doing for talking?
8 minutes, 10 minutes.
Left?
Yeah.
Okay. So the recommendations from the supercomputing white paper, I've said the first two, research-driven and sustainably developed. So the first one, research-driven, sustainably funded. We need to have some confidence that there's going to be a sustained level of funding, which we haven't had for many years, but which competitor countries do. We also wanted to deliver at all scales, so the idea would be that by the middle of the decade, we would have an exascale system, but that on the way to that we would have several staging points at the kind of 100 and then several hundred petaflop scales, so that we can build towards being ready to have a scientifically productive exascale system. Point one is to write a peer-reviewed UK supercomputing science case. So I was the lead author of the white paper, and my punishment for putting as the first thing we had to do was to write a science case was I was asked, well, go and write a science case. So I've been editing the supercomputing science case, and I'll talk briefly about that at the end, but that has now gone to peer review, so that's kind of starting the process of getting the funding. The technology program I'll talk about in a moment. Part three is make sure that we're fully engaged, that we don't lose contact with the actual research communities that we are supporting. So meetings like this are at the beginning of that process, making sure that everybody is bought into the roadmap and evolving it as our scientific requirements change. Then the fourth one is to bring everybody together in terms of the different communities, computational scientists, computational mathematicians, and the researchers using HPC to make sure that we have services which are as productive as possible. The software re-engineering I'll talk about in the software roadmap, exploring the opportunities for greater coordination. Again, I've mentioned that this joining up of the systems, and finally to have a call like Insight, so to allow the most ambitious program, so Insight was industry focused, but this would be also academic focused, essentially allowing people to do kind of grand challenge calculations on the new systems. So one of the recommendations, number 2, was this technology foresighting program, which I thought would be of relevance to people, the industry people in this room, as well as the researchers. The idea is to have an ongoing funded program where we can build proof of concept systems, so essentially co-invest with industry of various different technologies on various different scales. But the main thing would be to have access for all UKRI researchers and some industry partners, so non-IT industry partners. But rather than the approach that the UK has pretty much universally taken up until now, where we approach you and say, can we have some free stuff? And you very generously say, yes, you can have some free stuff if you give us some feedback. We'll actually be able to say, this is the kind of free stuff that we would like. Can we co-invest and come up with a program where we invest together? It'll also mean that we can target particular architectures for the future, and our software engineering teams can then be working towards those, so that the communities have time to get ready when we're deploying new systems. So the principles that we recommended in the white paper should be followed in terms of the design of the all the services. Again, research driven, and I know I'm saying that over and over again, but that's absolutely central for all the white papers. Is the basis for doing all of this is not just to have the most powerful computer in the world, it's to deliver the best science and research out of that system. So it's absolutely essential that we don't just build things because we can, that we build them because there's a specific research question or set of questions that we're trying to answer. And therefore the success is defined in terms of, is it productive? So does it produce papers, does it produce innovation, is industry able to use it to deliver the research that they need? And the other principle is, it's not just the hardware, we also need people, algorithm design, and software development. So we need the people to support them, and we need a lot of investment in that area. In terms of delivery, the most successful systems are community driven, so that there is an engagement between the research communities and the systems that are being built. Obviously value for money, so that's where the vendors can be very helpful in that side. It'll be co-designed with industry partners. Again, we're not just going to be buying off the shelf things, so there's value for both sides if we can work together in terms of the design. And there's many examples of that across the UK already. And it has to be supported by investment in people and skills. So the typical funding mechanism where a large amount of capital is dropped at a random time is very nice if you receive some of that capital, but then you have to scrabble around to find a way to power it and find money to pay people to run it. So we want to have it that there's a long-term strategy for funding. So this diagram is to replace previous diagrams. You've probably seen the usual pyramid diagram for the different tiers within a supercomputing ecosystem. And we decided to explicitly move away from that for a number of reasons. So you still have the tiers, named tiers, so tier 0, tier 1, tier 2, and tier 3. But we wanted to emphasize that the different tiers, the different scales of system within this ecosystem all depend on each other. So this is not a hierarchy where a junior researcher starts on a tier 3, goes to a tier 2, goes to a tier 1, and eventually, if they're good enough, they get onto the tier 0. Every systems at all scales are already delivering world-class science. Now, right now, we don't have anything in the tier 0 class in the UK, so that piece of the pie needs to be added, and that will be the exascale and the pre-exascale systems. But even once we have that, you need to have all the other scales as well, because sometimes you'll need to do simulations on the tier 1 systems to get ready for your tier 0. Sometimes you'll be analyzing the output from the tier 0 calculations. But often there are projects that do their entire workflow on a tier 1. And the main thing is we want to make sure that within the ecosystem, everybody has the appropriate tools to do their research. So if research needs exascale, we should have an exascale system that people can use. If it doesn't need exascale, we shouldn't be running it on an exascale system. We should be running it on one of the other ones. That would be more cost effective. So this is essentially what the roadmap will look like. It has funding for all different scales. Tier 3, so the local systems, were out of scope, which is why that piece of the pie is slightly offset. But they're obviously important in terms of training and delivering science from universities. But the plan is that all the other sectors would be funded as part of a funding process. And as I said, on the tier 0 side, the goal is by the middle of the next decade to have an exascale system, but that there are several points along the way leading to that, some of which are quite urgent. So, I'll now talk a little bit about the other white papers, because of the way that they, all the white papers feed together to deliver the overall planned ecosystem. So cloud is obviously a key aspect of how we might provide some of the services. So this diagram essentially shows the different scales and numbers of researchers involved, and the scales of systems on the y-axis. And the important thing here is that we would expect that cloud will play an important role in the UKRI ecosystem. The UKRI system, it'll be a mixture of public clouds, private clouds, and community clouds, so on different scales. But the important thing is that they should be interoperable, so nobody's locked into one particular thing. And it's important that the decisions on which type of system to use, whether it's on-prem or cloud, is again, it's based on the science workflows. So if it's the most appropriate, if commercial cloud is the most appropriate and cost-effective way to do a particular science calculation, that's the way we should be doing it. But it shouldn't mean that that community can only use public cloud. They should also be able to use on-prem if that's appropriate for some of their workflows. So this should be decided based on what's the most effective and most cost-effective way to deliver science from the national infrastructure. So the recommendations from the cloud white paper were, as I said, scientific and technical requirements must come first. No one should be forced to use the cloud just because it's the thing you should use. It should be that it's, again, the most appropriate research tool for particular science problems. We would expect that a mixture of on-prem and cloud will be part of the most cost-effective solution. But it does need a stable funding stream. It needs a stable funding stream and business models that can actually allow this, because at the moment the standard funding mechanisms are very difficult to interface with using public cloud. We also need to have a well-established process for looking at which workflows will operate on effectively on public cloud and which won't and why not. So it means there are some areas where we will probably need to keep local UK capability. So for example, in the larger scale HPC calculations, we'll want to keep the skills to be able to support those kind of calculations. And so they are ones where we want to be able to monitor what's going on in cloud, make sure that when it's most cost effective, that's what we're using, but otherwise, when the appropriate way to do it is locally, we want to be able to deliver that. And a key point is, from a strategic point of view, it's important to retain the skills in terms of people who know the research areas and can deliver the technical systems. It's very important that we keep those skills available in the UK. And so they are sets of skills that if you lose them, it's very hard to get them back. It says it could not be regained, but it's very easy to lose that community of expertise. It's very hard to get it back once it's gone. So, have I any time left?
Negative 20 seconds.
No, they have 5 more minutes.
Okay, I'll take that back. Okay, so algorithm, software, and skills. All the white papers effectively mention the key importance of software development and algorithms in terms of making sure we can use the systems. The headline vision is to make the UK the best country in the world in which to develop software. And what you'll note with several of these aims, or recommendations rather, is to create an environment which we don't currently have, or which is just beginning to appear, where software is rewarded. So software development is actually valued. So for example, UKRI should recognize the vital role of software in the research process. This is something that when large new projects are starting, it's important UKRI insist that the software requirements, be they using existing software or developing new software, those are built in and costed from the start. Not as is often done, where an entire project is planned and then shortly before it starts, it's realized, oh, we need some HPC, we need some skills, we need some software, so that it would be part of the process. And the other vital part is to make sure that there is a mechanism for people to develop careers in this area, because at the moment it's very hard. The research software engineer, that kind of career path is now developing. It's being more better recognized. But for example, in the ref, having written a really good piece of software that has become a community code is not necessarily something that's easy to incorporate into the ref, and it should be there need to be mechanisms developed so that we can include software in ref submissions, and that will help people develop their careers, and that will mean that we'll be able to retain people with the required skills to develop these. And so what's also needed in terms of funding is a software environment that ensures you can get software from being something which is initially thought of by an individual researcher all the way up to being a community code, if that's appropriate. And so at each stage in this pyramid, you have to put in funding. Most of this funding doesn't exist, so these are new funds that have to be found. So looking at algorithms, so actually explicitly funding algorithm development in particular areas to make sure that the right algorithms for the next generation science and the next generation hardware are being supported. And then at each stage, putting in additional funding in order to be able to, for example, here the Maximizing Impact Fund is to look at those codes which are growing and have the potential to become either products or community codes, and again, putting in the funding to keep that process going. And that's, so the software and skills white paper emphasised this is not free. This is something that actually costs money and needs planning. And if you look at what other countries have done in terms of software investment, it dwarfs the investment that's gone in the UK. And so it's something that has been done very effectively in the UK by many different people. But in terms of the funding that's directed at it, it's been very limited up to now. So the final white paper that I'll mention is the data one. So obviously data is a growing problem. The kind of numbers that we're talking about are enormous. So we're looking at 10 exabytes of data. So this is research data that will need to be curated by the end of by 2030. 10 exabytes in the physical sciences, 1,000 times current in life sciences, 60 exabytes in healthcare, and at least 2 of curated data. That's not the total storage requirement, that's just the simulation outputs that you want to keep for the long term. Obviously there's a lot more data generated and overwritten. And many of the projects that use data have to collaborate internationally, and there has to be processes to allow that. And there are many drivers in terms of different, now that data is becoming more widely available and more widely shared between healthcare and other areas and between industry and academia, there's many new questions that can be looked at, but all of these are driven by, all of these drive much larger volumes of data needing to be available. And again, coming back to this 2.4% investment, we really have to change how the UK looks at data, because at the moment data curation in many fields is very poor, and there are data sets around that are either not being used or are effectively lost to researchers. And if we're actually going to deliver this 2.4% investment, it means that we're going to have to recognise the value of the data, make it available so that people can actually use it. And the vision for the data roadmap is that there would be a research data infrastructure to support all the research that people want to do, and make the UK a leading country for research that's data intensive. And so the benefits or the requirements are all listed there. I think a key thing is the final one in terms of the transparency and trust in scientific method and results. That's very important, because again, the more the data sets can be cross-checked by others, the better the science will be, and the more trust people will have in the results. So the recommendations that followed in the white paper, so the goal is to create a thriving, strategically coordinated and federated UKRI research data infrastructure. And essentially a lot of it comes down to funding, as ever. There's been a lot of underfunding in this area. It needs to be reversed. So recognise that a very significant amount of funding, almost comparable to the funding required for supercomputing, is needed to kind of bring the UK back up to the levels it needs to be in terms of data and data processing. There should be a move to where it's sensible and appropriate and cost effective to combine data sets or combine provision and services. That is something that should be done. But there also needs to be more changes to the funding structure so that we can be more flexible in how we use the resources. A lot of work needs to be done on the policy side on how you actually coordinate this, especially internationally, to make sure that all the resources that we have are available within the UK and can be shared outside. And again, we have to change how things are costed so that data is seen as something which is fundamental to the research that's being done, and therefore it's not something that should come out of the research budget. It's basically part of the infrastructure cost of doing a research project. And so that's very important, so that even if an individual researcher is getting some funding to do a particular problem and there's a data cost associated with that, it needs to be identified that that's not coming out of essentially it's not reducing the number of postdocs you can have in order to be able to maintain a data set. So the final couple of recommendations, and then I'll end with the status of the roadmap, is that each sector needs to have its own well-defined data roadmap because data requirements are very sector-specific. So that's something that needs to be worked on urgently so that a proper plan can be drawn up. Globally, though, it's the scale of data curation that needs to be available by 2030 is 2 exabytes by 2025 and 10 by 2030. And again, investment in people, which was a theme of pretty much all the white papers. We need investment in research data professionals, which covers everybody from data scientists through the people who actually build the hardware, maintain it, develop the tools. So it's all aspects of data curation need investment in skilled people, and they need to be funded. So again, this is something where the software engineering funding schemes could be looked at as a way to develop the funding for research data professionals. So the final thing I'll say is just to say so I've kind of outlined the vision for the roadmap. It's very ambitious and requires a lot of funding. So what's the status of it? Well, at the moment it's awaiting ministerial approval for publication. So I have been told to say that, or to emphasize, the fact that it hasn't been published is not because there's a problem with the roadmap. It's, I shouldn't say there's a problem with the minister, but it's about we're waiting for permission for it to be published. And the key thing is it's not a funding roadmap yet. It is a roadmap of the ambition of the UK and across all aspects of eInfrastructure. So the next stage is to turn this into well, all of what's in there has been costed, but the next thing is to turn that into actual funding base. The good thing is that because it links in with this 2.4% R&D spend, there is a growing awareness across government, not just in the usual departments, that eInfrastructure is something that needs to be properly funded in the UK. I can see a few skeptical faces in the audience, but at least an awareness is a good start. And if you look at the progress report on the roadmap when it was published, eInfrastructure was mentioned several times as being absolutely key. Obviously that's just a progress report, but I think there's reason to be cautiously optimistic that at least now, by having eInfrastructure as a cross-cutting theme explicitly in the process, it means that we've now been able to properly raise awareness of what the requirements are. I think we really need to harness a huge amount of momentum has been built up across UKRI in putting these roadmaps together. It's nearly killed some of us, but a lot of work has gone into generating the white papers, generating the roadmap. So I think it's important that we keep that momentum going. So in the last 10 minutes, I will skip. So I was going to briefly go through the science case just to say there's a very exciting science case that has now been written and is out for peer review for supercomputing, and similar science cases will follow. I'm very happy to talk about that offline. But the conclusions are the roadmap is a very ambitious plan for the next 10 years. It covers all aspects of the infrastructure. It really did bring the communities together. Sometimes against their will, but now all the communities are working together. Underpinning everything are the science cases, so that the research cases will be at the heart of everything that's done in the UKRI planning around this. A lot of investment is needed, so it isn't going to be free, so make sure whenever you have an opportunity to let funders know that this requires investment, please take it and encourage them just to kind of prepare them for the kind of numbers we're going to be asking for. But a vital part of it is this is not just academia and the research communities within UKRI, it's also including industry. So it's great to have an event like today where we can kind of talk about what's in the roadmap, and but also I'd like to encourage you all to get involved in whatever capacity you're here today. Look out for the opportunities that will be coming up, and do get involved in delivering this, because it really needs to be something. If we're going to deliver the things that we would like to in terms of research and innovation by 2030, it needs everybody, not just everybody in this room, but all our communities to work together to deliver it. So thank you very much. I'll leave it there.